Hi everybody, Physics Ninja. Today I want to go and look at how to derive an equation for the efficiency of the Carnot cycle. In my previous video, we looked at a full Carnot cycle. I gave you pressure and volume at a couple points along the cycle. We filled out the table, and then we also looked at change in internal energy, heat either put in or taken out of the system, and also the work done for every process here. At the end of that video, I calculated the efficiency using this formula right here. 1 minus the ratio of the two isothermal temperatures, the cold temperature over the hot temperature. In this video, what I want to do is I'm just going to consider this general Carnot cycle. And I'm going to show you how you can prove that the efficiency is given by this equation. All right, so by the end of the video, you'll know where this equation comes from. And hopefully you can use this knowledge now to go calculate the efficiency of other cycles, other than the Carnot, maybe a Stirling, an Otto, or something else that appears on a PV diagram. All right, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. It's the best way to support what I do. All right, let's get started. All right, we're going to consider a generic Carnot cycle. It's shown here in the figure, and it's defined by 4 processes. So I start at, for example, some point A. I have an isothermal expansion. I'm going from small volume to larger volume. Isothermal means the temperature is constant everywhere from A to B. From B to C is something referred to as an adiabatic process. In this case, there is no heat exchange between the gas and the environment. Again, it is an expansion because I'm moving to the right on this figure. Now, C to D, on the other hand, is another isothermal process, but this is a compression of the gas. Okay, again, all that constant temperature down here. And our last one is another adiabatic process from D to A. In this case, compression again, and there is no heat exchange in adiabatic processes. Now, before I go and calculate the efficiency, what I'm going to use are 3 basic equations that I'm going to use in order to substitute into the efficiency equation. The first one, pretty well known to everybody, I hope, is ideal gas law, right? PV equals nRT. Pressure, volume, and temperature are state variables, right? Every point on this graph is represented by one value of P, one value of V, and one value of T for a gas. The second equation is very important. It's the first law of thermodynamics. It tells me that the change in internal energy of a gas, I could do it 2 ways. I could either put heat in or take heat out of the gas. Okay, that's defined by Q. Or I can let the gas or do work on the gas, or let the gas do work on me. Okay, so this is how I write it down. If I use a positive sign here, if I use positive for the work, it means I'm considering the work done on the gas. Some textbooks will use a negative sign, but usually if they do that, the work they are discussing is the work done by the gas. So those are opposites. Be careful with that. The third equation I'm going to use is the change in internal energy. There's something about this U value. U is also a state variable, okay? It's actually a variable that really only depends on the temperature of the gas. So that means if I'm looking at the change of internal energy, like in the first law of thermodynamics, I can write it only in terms of the change in temperature of that gas, okay? It's actually, I'll discuss this on the next slide. It doesn't depend on the path that you take the gas to calculate this change in internal energy. It only depends on the final value and the initial value of the gas, right? It doesn't depend on how you got there. Quantities like Q and the work, those ones depend on which path you take. All right, in the last bit, we're going to put everything together and look at the efficiency, which is defined by the work done by the gas in this case. So it'll be the opposite sign of the work done on the gas. And again, we're considering one full cycle here, divided by how much heat did you actually have to put into that cylinder in order to accomplish this much work. All right, let's go to the next page and start working on these processes. All right, just want to just say another minute or so on delta U here. Again, I said that U is a state variable, which is defined in terms of the temperature of that gas. And everywhere on this PV diagram here is defined by one temperature. So imagine you start over here at point A. Point A is defined with some initial temperature. And let's assume here that I work my way to point B. I can do that along different paths. It doesn't matter which path you take. You start at point A, and in all three cases, you finish at point B. So if somebody asked me for what is the change in internal energy for that black curve, well, I would say it would be the number of moles, that the heat capacity of the gas at constant volume, divided by delta T. So in this case, it would be my final temperature, TB, minus TA. That would be the change in internal energy going from A to B. Now, if I did it for the orange curve, again, I would say, again, A to B. And I would have the exact same value because it doesn't depend, although the path is considerably different, okay, my equation is going to be the exact same. I'm going to get the same change in internal energy of that gas regardless of which path you take. Okay, so the important thing for delta U is that it is path independent. The other thing that's really important is if you do one full cycle, imagine I go to here and then I come back along the blue line. All right, imagine I trace this cycle out. I go to TB and then I bring the gas back along this process over here. Since I started at TA and I finish at TA, my change in temperature here is going to be equal to 0 in that case. So for one cycle, as long as you go back to the original position, the change in internal energy for any closed cycle has to be equal to 0 because you start and you finish at the same place. All right, so that's it for delta U. Now let's go back to our Carnot cycle. All right, we're going to consider first the process going from point A to point B on this Carnot cycle. So this is, by definition, it's an isothermal process. Isothermal process means that the temperature is constant over here. The temperature everywhere on this process, I'm going to call it TH because it's just one number. TH stands for hot. Okay. Now, when we're going from A to B, we're interested in several different things. We're interested in what is the change in internal energy of the gas? Was there heat put in or out of the system? And does the gas do work or is there work done on the gas? So let's figure out how to calculate these three variables. Now, the easiest one is the change in internal energy, because remember, look at from equation 3. Change in internal energy has to be 0 because there is no change in temperature. The delta T is 0. So forget about that. So that's an easy one to calculate. The next one I'm going to do is the work. Okay, the work done on the gas. This is a definition. Now, since I'm considering on the gas and not by the gas, the definition is this. It's minus the integral of PdV. And I'm integrating here is where is my initial volume and where is my final volume. Okay, now how do you integrate this expression? Again, you're trying to find the area under the curve of the black line. But we're now going to use the ideal gas law in order to eliminate this p-value right here. All right, so all we do is you keep everything else the same. You keep the limits of integration the same. And the value of the pressure everywhere along this line, I use the ideal gas law. I can replace that by nRT, and which temperature is it? It's always at the constant temperature of TH divided by the volume. So this whole term here is simply that pressure from the ideal gas law, and I integrate that over dV. Now the next step I always like to do is, before I do the integral, I just bring all the constant terms to the front. So I have number of moles, the ideal gas constant, TH goes over here, and my last thing, I'm left with this integral from the initial volume to the final volume of dV over V. Okay, this is a well-known integral. It's given by the natural log, and when you substitute the limits here, you should get nRTH, natural log of my final volume, VB, over VA. Okay, now this ratio is going to be bigger than 1, so the natural log of a number that's bigger than 1 is going to be positive. But at the end of the day, the total work here done on the gas is going to be a negative value. Okay, that's because during an expansion, the gas does work, but the work done on the gas is going to be less than 0. Okay, negative value. So that's fine. Now, if you go back to the first law of thermodynamics, I can easily calculate what the Q value is. What is Q for this guy? Delta U is 0. I bring the work done on the gas on the other side. What am I left with? I'm simply left with this value, nRTH, natural log of VB over VA. guess what? Q for this is bigger than 0. What does that mean? That means you're adding, adding energy into the system, or adding heat into the system. So a lot of times here you represent that with just some arrow here, and this is how much heat I'm adding into the system for this isothermal expansion. Okay, so we have the 3 variables for that process. Let's now go and look at the adiabatic process B to C. All right, the next process going from B to C is something called adiabatic process. And by definition, for an adiabatic process, it means there is no heat exchange between the gas and the environment. So you set Q equals to 0 for that case. So what does that mean? If I go back to my first law of thermodynamics, it means that the change in internal energy of the gas has to be equal to the work done on the gas. So again, it's an expansion. So what do we know about the work done on the gas? The work done on the gas, it has to be a negative value because it's the gas that does work. Okay, so that means the temperature is going to get lower, right? Because our change in internal energy is also going to have the same sign as the work done on the gas, according to this equation right here. So before calculating this, let's remember that A to B was an isothermal process. We said all of this happened at one temperature. I called it T hot. Now, the process right after B to C is also an isothermal process. I'm going to call this another temperature. I'm going to call it TC, and you're going to see why in a minute, okay? Kind of jumping the gun a little bit, but everything along this orange line happens at the same temperature because it's isothermal. Okay, so that means the temperature at C is going to be this TC. I'm going to call it TC also. C in this case refers to a colder temperature than the one up above. So the reason I do this is because the change in internal energy is very easy to calculate for me, right? The change in internal energy of a gas is simply NCV multiplied by delta T. So for this process here, if I'm going from B all the way to C, guess what? It's NCV. What's my final temperature? It's going to be the temperature at point C. That is TC. And then minus, where did I start? My initial temperature was the temperature at point B. Well, that's the same thing everywhere along that black line. That is TH. Okay, so that means this is the change in internal energy for that process. Guess what? It is also the work done on the gas. NCV delta T, TC minus TH. So look what we have here. Now clearly TC is going to be smaller than TH because it's a colder temperature, right? So that means this work is going to be a negative value, and also the change in internal energy is going to be a negative value. All right, that's it. Now we're going to go back and finish these 2 processes. Let's go look at the next one now. All right, going from C to D now is again an isothermal process. We've defined it right here. Guess what? Those are easy to do, right? The change in internal energy, if the temperature is constant, has to be equal to 0. Again, my heat then must be equal to minus the work done on the gas. All right, now let's consider it. For this is a compression, right? So this is, let me just write that down. For a compression, guess what? The work done on the gas has to be positive, because the force done by the external agent on the piston is in the same direction as the displacement. So the work done on the gas must be bigger than 0. But look at, you have a negative sign right here. All right, you have this second value that's not highlighted here. The work done on the gas is positive. So guess what? The heat, in this case, the heat will be less than 0. It's negative. The way we represent that, it means there is heat that leaves the system. Heat leaves gas. The way you typically represent that is through another arrow. So we have energy going out, right? We had energy going in for the top isothermal process, right? That was heat going in. Now we have energy going out. All right, now how do we calculate Q and the work done on the gas, for example? Well, it's exactly the same way because it's an isothermal process. So what I could do is I can use the expression I had previously. So let's go ahead and just write it down. So what did I have? I had minus NR The temperature now is not TH anymore. It's going to happen over TC. And now it's the natural log of my final volume divided by my initial volume. Okay. Now let's just substitute what the final value is instead of writing this and this. My final value for this process is VD, and my initial volume is VC, all right, given from the diagram. Now keep in mind that VD is a smaller volume than VC. You can see from this diagram, right? The point D is all the way down over here. So this ratio here that appears is actually going to be less than 1, right? VD divided by VC is going to be less than 1. The natural log of a fraction, something that's less than 1, is a negative value. So that is what's going to take care of this thing. So if you wanted to here, and this is kind of something I just prefer doing, I just like absorbing that negative sign here and using properties of the natural log, I can write it down as VC over VD. So now clearly this guy here is going to be a positive value, and you can see the work done on the gas is clearly a positive value, right? This here is bigger than 0. And the last thing at the end to calculate the heat, it's just minus that value, right? So that's very easy to do. So Q, let's just write Q leaving the system now is going to be minus NR TC natural log of VC over VB. All right, we've got one more process to look at, then we can put it all together. All right, going from C to D now is again an isothermal process. We've defined it right here. Guess what? Those are easy to do, right? The change in internal energy, if the temperature is constant, has to be equal to 0. Again, my heat then must be equal to minus the work done on the gas. All right, now let's consider it. 4A, this is a compression, right? So this is, let me just write that down. For a compression, guess what? The work done on the gas has to be positive, because the force done by the external agent on the piston is in the same direction as the displacement. So the work done on the gas must be bigger than 0. But look at, you have a negative sign right here. All right, you have this second value that's not highlighted here. The work done on the gas is positive. So guess what? The heat, in this case, the heat will be less than 0. It's negative. The way we represent that, it means there is heat that leaves the system. Heat leaves gas. The way you typically represent that is through another arrow. So we have energy going out, right? We had energy going in for the top isothermal process, right? That was heat going in. Now we have energy going out. All right, now how do we calculate Q and the work done on the gas, for example? Well, it's exactly the same way because it's an isothermal process. So what I could do is I can use the expression I had previously. So let's go ahead and just write it down. So what did I have? I had minus NR. The temperature now is not TH anymore. It's going to happen over TC. And now it's the natural log of my final volume divided by my initial volume. Okay. Now let's just substitute what the final value is instead of writing this and this. My final value for this process is VD, and my initial volume is VC, all right, given from the diagram. Now keep in mind that VD is a smaller volume than VC. You can see from this diagram, right? The point D is all the way down over here. So this ratio here that appears is actually going to be less than 1, right? VD divided by VC is going to be less than 1. The natural log of a fraction, something that's less than 1, is a negative value. So that is what's going to take care of this thing. So if you wanted to here, and this is kind of something I just prefer doing, I just like absorbing that negative sign here and using properties of the natural log, I can write it down as VC over VD. So now clearly this guy here is going to be a positive value, and you can see the work done on the gas is clearly a positive value, right? This here is bigger than 0. And the last thing at the end to calculate the heat, it's just minus that value, right? So that's very easy to do. So Q, let's just write Q leaving the system now is going to be minus NR TC natural log of VC over VB. All right, we've got one more process to look at, then we can put it all together. All right, we now go from D to A. This is, by definition, an adiabatic process for the Carnot cycle. this automatically means that there is no heat leaving or going into the system. That simplifies our first law of thermodynamics. It means the change in internal energy is equal to the work done on the gas. Now, for this process, it's very, very easy to calculate the change in internal energy because we know what the final temperature is and we know what the initial temperature is. Using equation 3 right here, NCV, again, T final minus T initial. T final is T hot minus T initial. That's it. That is the change in internal energy going from D to A. Now, is this number positive or negative? Again, just look at the change in temperature. T hot is going to be bigger than T cold, so the change in internal energy here goes up. So how can I change the internal energy? Then look at my first law of thermodynamics. The only way I can do that is if the change in internal energy is equal to the work done on the gas. Clearly, the work done on the gas must also be bigger than 0, right? That's where it gets the energy from, to change the internal energy of the gas. So it's very easy now to calculate the work done on the gas. All you have to do is set it equal to the change in internal energy. So it's also NCV TH minus TC. Now we're all done. We've calculated the 3 quantities for this process, this adiabatic process going from D to A. So now what we have to do is we are now in a better position to start looking at equation 4 to calculate the efficiency. Okay, let's kind of summarize our 4 processes. Let me put everything in a table so we can clearly see it. All right, here's the summary table for all the 4 processes that we just calculated. Clearly, there's some easy cases. For example, A to B and B to C. We know isothermal, just put the zeros in there. For adiabatic, B to C and D to A, we put in the 0 for the heat transfer. We calculated the work for all the 4 processes, right? So we've got those. Again, if you look at these closely, for example, if I look at the work from B to C, and I look at the work from D to A, they're exactly, one's positive and one's negative, right? The first one here is negative, and this is going to be positive, but they're going to be the exact same number for both of those. Likewise, for the change in internal energy, right? One of them's positive, right? D to A is positive. I increase the internal energy when I go from a cold to a hot. And yeah, so just keep that in mind, because at the end, really what we're going to be interested in is, well, what if I consider the whole process, go through all of these 4 processes? If I add all the quantities together, well, look what happens, right? If I add up all the quantities for the change in internal energy, we said it's a state variable. So I go back to the same temperature, there is no overall change in internal energy. Now, if I go ahead and calculate the heat, I know that there is heat going into the system over here. That was Q in. And then we said there was some heat leaving the system. So that's represented by a negative number. That's Q out, right? So you can go ahead and calculate what the total heat in is going to be, right? Again, what you have to do is simply sum up everything in this center column over here, right? So again, you would simply have nRTH, this natural log of VB over VA. Now I run out of space here, so I'll just write it right underneath, but it's minus nRTC, natural log of VC over VD. Okay, so that's the total heat. Heat in is going to be a positive number at the end of the day. Now, what else do we have? Last thing is we wanted to know the total work done on the gas for this entire process. You'd have to add all these 3 quantities out. But again, as I just mentioned, these are going to cancel, right? Anything with the isothermal process happens between those 2 temperatures. Both of these, when you add them up, they are going to cancel each other out. And all you're left with then are the same quantities you just added up, but the signs are going to be flipped, right? So you're simply going to have like minus nRTH, natural log of VB over VA. And then what else? Plus nRTC, natural log of VC over VD. All right, so now we know everything here for the cyclic process. We are in a much better position now to go calculate the efficiency. So let's go ahead and do that now. All right, so here's what we have. The heat that goes into the system for that first process, A to B, is given by this quantity. The work done on the gas, we calculated. We just simply added them all up. It reduced to this. Now we go and calculate the efficiency, right? So we simply use the definition, equation 4. Now this is where it becomes very crucial here. We write by the gas. It's not on the gas, and this is Q in. Now the work done by the gas is related to this guy. It's the exact opposite, all right? It's negative of this value. So we have to be very careful when you substitute things in here. So I'm going to change the signs everywhere, okay? Because I have by the gas here. So just keep that in mind. So that means this term here becomes NR TH natural log of VB over VA. All right, what else? Now minus NR TC natural log of VC over VD. All of this gets divided now by the amount of heat that you put in. That's the green equation here. NR TH natural log of VB over VA. All right, well, we could simplify this quite a bit here. Let me use my pen. All of the NRs can leave, right? They're in all the terms. What else? This first term looks exactly like this denominator term. Right, so you could certainly simplify that term quite a bit. So let's go ahead then and do one extra step. So if I divide through, I'm going to get 1 for this term because everything, TH natural log of VB over VA is exactly this. Minus. Now I'm left with this ratio of temperatures, TC over TH, and we've seen that before. The same equation I used in the other video. However, we still have these terms. You can't neglect this, natural log of VC over VD and over, oh boy, I'm running out of space, natural log of VB over VA. All right, we still have to worry about this ratio of the natural logs. So now let's go on the next page and work this equation out a little bit more and try to simplify this expression here involving these natural logs. All right, the question now, can we reduce this or can we simplify this ratio of natural logs? And the question is yes. The answer to the question is yes. I'll show you how to do that. For adiabatic processes, not only is the heat as 0, but there's also other relationships you can derive for adiabatic processes. You could write it like this. The pressure multiplied by the volume raised to this power of gamma, and gamma takes a very specific value of, at least for an ideal gas law, it ends up being 5/3. It's the ratio of specific heats at constant pressure over constant volumes. Now you could eliminate pressure or volume using the ideal gas law. For example, if I write it in terms of temperature, I could do a T, V to the gamma minus 1 is also equals to a constant. And anyway, this is the one I'm going to use right now. I can also write an expression just without volume, for example. But let's use this one right here, and you're going to see why. Because I want to eliminate these ratios here somehow, or I want to simplify them. So what we're going to do here is we're going to consider writing down this highlighted equation here for 2 adiabatic processes. That's where this formula is applicable. So for example, if I write it from B to C, well, if I start at point B, that's at a temperature T hot, and the volume is some value VB, and I have to raise that to the gamma minus 1. That must be equal to this product here at point C, since it's a constant value. It's a different temperature over there. It's called TC, and the volume is different as well. So it's not VB. Silly me. It's VC. Again, to the gamma minus 1. So that's one expression. Now that has to be, I can write another expression now for another adiabatic process. So what if I go from D to A, right? So everything at point A has to be equal to everything at point D. So here I would have T hot for point A, and that here has a volume VA, gamma minus 1. And this here has a temperature TC at point D, and the volume is D gamma minus 1. Now, what we can do now is, what if I take the ratio of both of those? Because all of these expressions here involve ratios of volumes. Look what happens if I do that. The temperatures THs are going to cancel, and I'm going to be left with this. VB over VA to the gamma minus 1 has to be equal to VC over VD, also raised to the gamma minus 1. Well, the only way this is possible, right, is if this ratio is exactly the same, right? If VB over VA is actually equal to VC over VD. Let me clean that up a little bit. And look at this ratio right here. That is exactly the same ratio that appears, right? It means that this is exactly equal to this, right? VD over VC is VB over VA. So that means that both of those logarithms, you can cancel them out, right? There is nothing special about them. They're the exact same value. So at the end, we're left with the efficiency of that Carnot cycle is 1 minus TC over TH, right? Kind of a nice simplified expression for this cyclic process. All right, in the last bit of the video, this is kind of all I wanted to do, but let's go ahead and show why you have these expressions over here for an adiabatic process if you're interested in seeing how that's done. All right, so the last bit I want to do, I'm going to go over this quickly here, but consider like a little bit of an adiabatic process. So you have there's no heat exchange, so you have dq equals to 0. The first law then reduces to a little bit of change in energy must be equal to the work done, a little bit of work done by the gas. Okay, so now we substitute some values. So for du, we have N CV, and the change in temperature is dt, and the work done by the gas is minus PdV. All right, now we have a whole bunch of variables here. We have all the three variables kind of contained in one equation, T, pressure, and volume. So we have to try to eliminate that. And the way I do that is using ideal gas law. Okay, so what if you take the differential of this? So if I differentiate this, I would have V dP plus V, not V rather, PdV. All right, this is just using the chain rule here, equals to NR dt. All right, so again, my goal is to eliminate temperature. I have similar terms. I have to bring the R here at the bottom. Let's get rid of that term and let's put it down here like this. So now I have N multiplied by delta T. That term also appears over here on the left-hand side. Now I got to be careful. I have this additional specific heat here. So let's go ahead and do that. So take out the specific heat. And now N multiplied by dt is everything here on the left-hand side of the second equation. So it's VdP plus PdV over R equals to, again, the right-hand side here minus PdV. Okay, so we can group some of the terms. Let's bring everything on the left-hand side and group some of the terms. So again, I have two delta V terms, right? Here's one and here's going to be the other. So if I group both of those, what do I get? I get CV over R. When this goes on the other side, it becomes plus 1. And I factor out the pressure and the change in volume, the small change in volume. And what else? Now I also have a term over here, right? So I have plus CV over R, and this becomes VdP. Okay, doing pretty good. What you can do here, let's go over here on this side. What I'm going to do here is just change that constant. I'll write it as CV plus R, everything over R, PdV, plus CV over R, and VdP. All right, so now we're going to do a couple things. First of all, I'm going to define something else. This is the specific heat here. You can see if the pressure is constant, this term here goes to 0. So I'm going to call this CP. We're going to call that CV plus R. Okay, this is just a definition, just another constant, just to clean up the math. Now the other thing you see is that R is in both terms here in the denominator. You could just get rid of that. Okay, so my first equation now becomes CP PdV, this upper equation, plus CV VdP. All right, and that's equal to 0. Now what I'm going to do is just divide through by CV. I want to introduce that constant gamma here that I just quoted here, so I can get rid of this term now, get rid of that. And now this guy here is simply equal to gamma. So we keep going. So now we have a gamma PdV plus V dP equals to 0. All right, we're not quite done. Now, what last thing you can do here is divide through by pressure times volume. Divide both terms by pressure times volume. And what that does for us now, it'll eliminate pressure on this term, it'll eliminate volume on this term. And one of the last expressions I have now, it's dV over V plus dP over P equals to 0. All right, so now you have to integrate this expression, right? So I integrate here from some initial volume to some final volume. I integrate this term from some initial pressure to some final pressure, okay? What you end up getting here is gamma. This is the natural log of VF over VI, right? And this here becomes plus natural log of final pressure over initial pressure equals to 0. Now I have to use some properties of logarithms. If I have an exponent in the front like gamma right here, I can get rid of it as long as I put it over here to the gamma over here. And what else? Now I use the property of, right, both of those terms. What you can end up doing now is just group them together in one natural log function, right? So you get natural log of final pressure, VF to the gamma equals initial pressure, V initial to the gamma. That has to be equal to 0. The only way this is equal to 0 is if I go to the final expression over here, is if the natural log is equal to 1. So that means that the pressure initial, volume initial to the gamma minus, to the gamma rather, not gamma minus 1. Well, it's a long video here, bear with me, is PF VF to the gamma. You can also write this as just being equal to some constant. It's constant everywhere along that adiabatic process. Okay, the last little bit is if you wanted to, for example, eliminate pressure and just have it in terms of temperature and volume, that might be something you're interested in. Let me show you how to do that. All right, so you start with that first expression. If I wanted to write it in terms of temperature and volume, well, you have to eliminate pressure. The way I eliminate pressure is simply using ideal gas law, okay? So instead of writing pressure, I write nRT divided by volume. So all you do now is group all the constants on one side, right? So you have my original constant and divided by nR. Those are two other constants. And what I'm left with here is T, and then this becomes V to the gamma minus 1. So here you can call this a different constant, constant star, okay? So that is the second expression, right? TV equals to some other constant. If I wanted to eliminate, for example, volume, well, so you keep pressure the way it is. Now instead of writing volume, what you do is you use ideal gas law. So you write it as nRT and divided by the pressure, okay? And this has to be equal to that first constant I had up here. Now you write this through. So what do you have? You have P to the 1 minus gamma is the exponent. This becomes T to the gamma. And the rest here becomes some new constant, different from the previous one, right? This is constant 2 stars. All right, so this is how you can write kind of 3 different expressions for adiabatic processes involving the different variables and this new quantity that we called gamma, which is related to the specific heats either at constant pressure and constant volume, right? The ratio of both of those is how you define that gamma value. All right, that's it for me, folks. Thanks for watching.